A hyperbola is a set of all points, x and y, in a plane. The difference of whose distances from two distinct fixed points, the foci, is a positive constant.
In the diagram, we see that the two foci are labeled, and any point on the parabola, the difference of these two distances to the two foci is always the same positive number. In the second diagram, we can see other points that are labeled, including the vertex, the center, and the transverse axis.
There are two standard forms of the equation of a hyperbola, with center at h and k. One's transverse axis is horizontal, which is x minus h squared over a squared minus y minus k squared over b squared equal 1. And another one is transverse axis is vertical, which is y minus k squared over a squared minus x minus h squared over b squared and equal 1.
The difference between a horizontal transverse axis and a vertical transverse axis is which variable comes first in the equation. Are we basing it off the x variable or are we basing it off the y variable? It is different values within the hyperbola.
In the graph's equation provided, we just have to look at two variables, which is a and c. And in the case of hyperbolas, a times c has to be less than 0, which means that a and c needs to have unlike signs. The degenerate form of hyperbola is two intersecting lines. One interesting property of hyperbolas is that they have a reflecting property which can be used in real-life applications. For example, it is used in radio direction finding since the difference in signals from two towers is constant along the hyperbola, and in the construction of mirrors inside telescopes to reflect light coming from the parabolic mirror to the eyepiece.
Another use is the hyperbolic mirrors. These mirrors can concentrate light into the focus point of the hyperbola. With this, people can cook stuff without a fire. Satellite dishes also work in the same way, concentrating signals instead of light. And with these mirrors as lens, people can create very interesting images such as these. As you can see from the diagram, using a parabola, we can calculate the distances in which the signals arrive, and with that, we can calculate where exactly the point is. This is what we use for a GPS locating system. The trail of shadow in which the pointer of the sundial creates is in the shape of a hyperbola. Thus, with the correct calculations, one can calculate the exact time of the day by calculating the points on the parabola. This is the resulting image from the sundial's path on summer solstice.
When an airplane travels faster than the speed of sound, which is 340 meters per second, the sound waves from the cone behind the airplane. If the airplane is flying parallel to the ground, the sound waves intersect the ground in the hyperbola with the airplane directly above its center. A sonic boom is heard along the hyperbola. If you heard a sonic boom that is audible along a hyperbola with the equation x squared divided by 100 minus y squared divided by 4 equals 1, where x and y are measured in miles. What is the shortest horizontal distance you could be to the airplane? As you can see, the equation provided lacks h and k. That's why the plane is at the origin. And because the x squared is in front of y squared, the transverse axis is horizontal. And so our graph will look something like this. And the answer is 10 miles.